Welcome back to the channel, everyone. I decided to recut this video. Some of you might have seen Simplicity is Hard Work, Part 1. I decided to recut it. There were some errors in the video. I didn't like some of the audio quality, so I'm trying to improve that. And also wanted to just do both parts 1 and 2 in a single video. So here we go. Today we're going to be talking about one of the most, the criticism I hear most about Foundry, which is that it's too expensive, right? But if you actually do a total cost of ownership breakdown that includes the activities that go around trying to engineer Foundry-like systems on your own using hyperscalers, using other technology, the costs are way, way higher. The likelihood of failure is also way, way higher. These are the same companies that are failing with digital transformation at a 70% rate or an 80% rate, depending on who you ask. And that's because software by its very nature is just complicated. And by Palantir providing this layer of abstraction, this sort of cloud operating system that sits above and manages all that complexity on your behalf, you're actually not only able to focus on business outcomes and what matters for your company, but you're able to do it much faster, and you're able to avoid all of this additional cost and also the opportunity cost you pay for failure. So get ready, here we go. So first, let's get into a little bit of background on software complexity and how you measure it. So we're going to go back to some OGs in the computer science space. The first is Manny Lehman and Lehman's laws of software evolution, right? And basically, you can distill these laws down into the phrase that the more code you add, the harder it becomes to add more code. And I'll leave a link to wikis and all the source material used here. And this is undeniably true. And it's an observation that software has this natural emergent complexity in it as things start to interact, and the number of paths, possible execution paths increases. And a lot of work has gone into how do we measure complexity in a software system after these sort of observations about how they evolve and how they sort of naturally become way, way, way more complex. One is cyclomatic complexity. Cyclomatic complexity measures the number of linear independent paths throughout a program, right? And it's calculated based on the control flow graph of that program, where each node represents a block of code and each edge represents a control flow path. The best way to think about this, though, is it grows linearly with the number of if-else statement or if statements, for loops, switch case statements, etc. And you're basically adding a point for each of these things, right? And it generally grows linearly. And again, I'll leave a link to the source material here. And the other way that we measure complexity, or at least one of the other ways we measure complexity, is end-path complexity, right? The thing with end-path complexity is it's measuring the total number of acyclic execution paths throughout the program. And this is exponential, right? So end-path complexity could easily get extremely out of hand. And I'm going to read this one quote for you. So end-path complexity is exponential, and in old legacy code, don't be surprised if you find functions with complexity over 100,000, right? So, and that's insane, because the default you're shooting for is 200, right? And so these two methods are a really good way to just easily observe and calculate you go to GitHub, look at any project, and you can start to get an idea that even simple programs are insanely complex. And to give you an idea of just how hard it is or just how complex they are, we can look at the other side of this, which is exhaustive testing, right? And why exhaustive testing is generally impossible. It's directly related to both, how we measure complexity, either end-path or cyclomatic. There's some great work, and again, I'll leave a link to both of these papers. But exhaustive testing a simple program to add only 2 integer inputs of 32 bits, yielding 2 to the 64 distinct test cases would take hundreds of years, even if tests were performed at a rate of 1,000 per second, right? So this is, in my opinion, what really puts software complexity into perspective, is that to actually exhaustively test every path in this program, and for very simple programs, right, is just not achievable. And Roger S. Pressman, I'll leave a link to his work. This guy's work's incredible. He's done a lot, and just documenting software development practices, testing practices, etc. But I love this example he gives in this paper. Consider a 100-line program in the language C. After some basic data declarations, the program contains two nested loops that execute from 1 to 20 times each, depending on conditions specified at input. Inside the interior loop, 4 if-then-else constructs are required. There are approximately 10 to the 14 possible paths that may be executed in this program. To put that number in perspective, we assume that a magic processor has been developed for exhaustive testing. The processor can develop a test case, execute it, and evaluate the results in 1 millisecond. Working 24 hours a day, 365 days a year, the processor would work for 3,170 years to test this program. That is absolutely insane stuff. So if you're not understanding just how like insane software complexity is and how insanely hard it is going to be to manage, because you can't test your way out of this problem, then I don't know what to tell you, right? And so the hardest freaking thing to do in engineering is to keep things simple. It takes a lot of experience, takes a lot of education, takes learning from extremely talented engineers who've come before you and know how to deal with these problems, because there's no one way to do this. There's not like and there are some techniques, and we have best practice, and we have lots of software engine like patterns to draw from, but at the end of the day, you really, this is about an experience. And so I love this quote by Rich Hickey, who's like an OG in the community, computer scientist. He wrote this quote a while ago, and it's simplicity is hard work, but there's a huge payoff. The person who has a genuinely simpler system, a system made out of genuinely simpler parts, is going to be able to affect the greatest change with the least amount of work. He's going to kick your ass. He's going to spend more time simplifying things up front, and in the long haul, he's going to wipe the plate with you, because he'll have the ability to change things while you're struggling to push elephants around. Now, anyone who's worked on a legacy code base at any company you've ever been to will attest to this. This is insane. And it's because companies often don't think about the cost and trade-off of adding more code or adding more features or whatever it is, and how they're going to manage complexity, and just how freaking hard that is. Which is why, generally speaking, you see platforms emerge that do it for you. You could point to the explosion of SaaS products. You could point to other point solutions that have taken off, and it's because there's kind of only one way to build software at scale correctly, and you get these companies who specialize in it and get all the best talent to build those systems and manage complexity on your behalf, right? And I believe that's what Palantir is for this layer above the cloud. And we're going to get into now a little bit about how do we measure cloud complexity, right? This is one thing to have a bunch of methods around software complexity, but no one's really talking about cloud complexity and why we need a layer above the cloud, which I've heard referred to as Sky Compute by the CEO of Databricks, but call it what you want. Palantir's kind of saying this like, we're the, the cloud was for infrastructure, we're the new thing for backend. I don't kind of like that. I think it literally is about providing an abstraction layer over the cloud to manage the complexity of these architectures you're going to need to deploy an app and provide all the things you generally need as part of that architecture, whether it's, transactional databases, columnar databases, full text indexes, simulation capabilities, or just something as simple as API gateways and functions and et cetera. So, and then there's things like eventing and loosely coupling all those things together. Like Foundry takes all that complexity that's typically in the cloud and manages it on your behalf. So next, let's kind of take it. I'm going to kind of break down the components of cloud complexity. And I'm going to use a simple test case of like a Hello World Lambda to show you like just how complicated it is to like deploy one line of code. And then we'll talk about how that is done in Foundry. And then we'll talk about like, okay, now that Foundry manages this complexity on your behalf and helps improve outcomes, like reduces failure rates, etc., why in the hell is no one talking about this and including that in their estimates of why they think Foundry is, quote, expensive? It's like, no, Foundry, when you compare it to all of these things we're about to get into, is astronomically cheaper, and the outcomes are astronomically better. All right, so let's talk about measuring the complexity of the cloud, right? So I'm going to break down just a few problems with uncovering this. One is just the control plane, right? And so like every cloud provider has their own control plane, and you can think of the control plane as like their way they talk about and declare components of the infrastructure and how you define their properties and provision them, etc. So there's a whole control plane around that, and every cloud provider is different, right? They you might see like some similarities, but for the most part, they are extremely different in the way they talk about things and their concepts. And I'm most familiar with AWS. I've done a tiny bit of work in GCP and virtually like none in Azure, but I work with a lot of professionals in that space. We're able to kind of have similar architectures, but the control planes are vastly different. And that's why you have like technologies like Terraform that have been created to try and simplify some of that. But just understand that control plane code and like how you provision infrastructure and deploy things is extremely complicated. Number one, it's extremely verbose, and like there's a ton of material you have to get through. I also think this is one of the biggest areas for AI companies. Like if you're building an AI startup, why is no one like building an infrastructure from code company that could just train models to write infrastructure as code and infer what you need from your code base? So if anyone wants to build that, that's probably $1 billion startup idea. Get to work on it. But just understand that's one component, and there's lots. You'd have to measure all that complexity because certain services are way more complicated to deploy than others. There's also things like networking infrastructure and security that are much harder to wrap your brain around in a lot of cases as well. Things like account vending machines that are also complicated. Most of the time in the cloud, you sort of separate things by account. So like teams might get a sandbox, which is like a separate account. You might have a dev account or QA account, but all of that is insanely complicated and hard to define. So that's like one component. The other is typically the cloud is based on microservices, and that is called distributed system hell. And for people who aren't familiar with distributed software systems, let me just state one of the things that people often overlook is that by definition, distributed software systems are complex systems, like the fucking weather, right? Like that's a complex system. And the only way you know anything about a complex system is by interacting with it. You actually can't compute the behavior of the system at a time. Like maybe you can over a short window, right? But these are really complicated things, and you actually can't compute the outcome. You have to interact with the system, observe it, and anyone who's worked with distributed software systems know this is just innately true. You never know what is really going to happen when you deploy a change or interact with the system, and so you just have to observe it. And again, this is and this gets even better because typical cloud architectures advocate for eventing or event-driven architectures where you loosely couple components of the system together and trigger them via the propagation of events through the system. And I kind of refer to this as the ninth circle of hell because eventing just with distributed systems is about the most complicated thing you could frickin' do, right? So like, and just as a simple example of that, most of these eventing systems are guaranteed at least once delivery. What does that mean? It means you get the same event twice, right? And you either have to have an idempotent function, meaning you can execute it multiple times and it won't leave the system in a corrupt state, or you do something that is more common, which are like distributed locks with Redis, and you have to have fencing guarantees with that. Just this standard like mutex, basically, if you can think of a mutex as like the key to a bathroom, right? Like one person takes the key off the hook, goes to the bathroom, comes back, puts the key back on the hook, then the next person can go. And these distributed locks ensure you don't like process the same transaction twice or engage in a new execution while the current one is running. And a lot of people at these companies that I go to don't even know this stuff exists, right? Like it's not the companies I go to, it's the companies I've worked for in the past. It's like you don't even figure these things out in a lot of cases until you run into a problem. You're like, oh crap, this is a distributed locks problem. You're like, no. And so it's really dangerous when you have like people who are architecting systems and designing initiatives and they're not accounting for these things, right? So like if you're at a company and there's these crazy architecture diagrams and no one's talking about all of the underlying complexity that has to be managed as a result of building this Rube Goldberg machine, you should realize those people are very dangerous, right? They are the ones that are going to lead to massive failures, and it's not their fault. It's just that a lot of the stuff is hidden beneath the surface until you've actually gone and done this multiple times. You don't know those landmines are there because the cloud providers aren't talking about it, and very few people in the industry are talking about it, you know. And I think more and more that's like surfacing as people have gone through the same journeys as everyone else. So like think in the last few years, a lot more companies have gone cloud native, a lot more apps are being built, and a lot more developers are discovering that this shit is hard, you know. So we're going to dive into a simple example. Let's just take a case of a Hello World Lambda, and I'll see if I can find code examples for this. I don't want to spend my time writing it, so if not, I'll put in pretty pictures over this audio. But let's just walk through what a simple Hello World Lambda is. And this is just a one-line program. It's going to print Hello World. Okay, that's it. That's all it's going to do. And let's just break down the components of this thing real quick, as someone has deployed these multiple times, just so you kind of get an idea of the complexity of actually deploying a one-line program to the cloud. And the one line, you can think of the one line that prints Hello World, that delivers, say, $1 of business value. All right, and that's going to be the only line in this that delivers any business value. So get ready. So we got the code that actually delivers the business value, but the next is the local developer tools you're going to need to test it, right? So I want to test my program. Maybe I want to design a simple integration test or maybe a unit test. How do I do that, right? Because this thing has to be deployed out into the cloud. Well, there's a whole set of developer tools that have been built for this, and I built my own in a lot of cases, AWS mocks. A lot of people don't know it, but you can point your AWS SDK instance to localhost, for example, and you can mock your own APIs by copying the service result, the headers and service results from an actual call and putting that into like a node mock. There's framework tools for this for local development. AWS has its own. I forget the name of this SDK that they've advocated for. There's also companies like the Serverless Framework, for example, that provide a lot of tools for doing this. And so you got to have that, right? And that's a whole set of tooling. So that's like up the complexity bar, because now your software tool chain is way more complicated, right? So that's just step one, local development and testing. The next one, right? Step two here, the control plane code, right? So I got to deploy it. Now I got to write all this control plane code, and I got to choose, do I want CloudFormation? Do I want something like the Serverless Framework, which is an abstraction and it's an open source project? It's maintained by community. I want Terraform from HashiCorp. Like, what am I going to use? Most people offer Terraform because it is simpler and it's got enterprise support. So maybe I end up using that or whatever. But now I got to write all of this complicated control plane code, and I got to test that, and I got to make sure it actually works, right? So like, okay, complexity upped again. Remember, it's a one-line program. Next thing I need is a CI/CD system to run that control plane code and actually deploy this freaking application. All right, so now I got GitHub Actions or Circle CI or AWS Code Deploy. Got to get that service up and running. Got to make sure that my workflows actually work, right? I got to observe those workflows and look for failures, right? So and I typically want to execute my unit tests as part of that CI/CD, or my integration tests as part of the CI/CD. Some of them happen before deployment. Some of those tests happen after deployment. That by itself, like, I had platform engineering teams that did nothing but build the CI/CD pipelines, and these are extremely talented, extremely high-paid engineers, and their only job was to maintain these CI/CD pipelines, because as it turns out, as soon as you start getting about 15 or 20 engineers contributing to the same project, then you start to run into problems like, oh, it takes an hour to deploy, and we have 50 merges per day. You know, how do you deal with that problem? Right, and that becomes a merge train. Right? I don't know if anyone knows what a merge train is, but there's some great work from, what is the company? It's not GitHub. It's, I forget the name of the. It's like, I'm blanking right now. GitLab. GitLab has a merge train, and the basic idea is you can parallelize merges, and you're basically doing a first in wins kind of strategy. And it allows you to more quickly get changes into production, so you're not bottlenecked by how long the CI/CD pipeline, not bottlenecked as much by how long it takes to run that CI/CD pipeline. That's hugely complicated. You can look at GitLab's merge train algorithm if you want, but this is like, the complexity meter is going through the roof at this point. And then the next thing you need, as this thing is deploying, is you're going to need a secrets manager, right? You need some way to inject secrets, whether they're database credentials or whatever, so that you can access a lot of these secure resources, right? So that's a whole nother thing. And yeah, GitHub provides a secrets management system, so does Circle CI. Most companies, though, opt to maintain secrets inside something like AWS Secrets Manager. They want to consolidate those things. They also want to provide rotation. So like, and depending on the control plane you're working in, a lot of times the dynamic injection of secrets isn't something that is abstracted for you. You generally have to like inject that code specifically. So you're going to be writing like whatever the control plane is for AWS would be CloudFormation to deal with a lot of that. And so that's a whole nother layer of complexity. Now, okay, this is just to deploy a one-line fucking application, right? It's like all these things that come in. And then the next thing you need are networking security. You need security around the network layer, right? Because if I deploy this Hello World Lambda to the public Lambda VPC, the shared VPC in AWS, means the internet is open by default, right? That is a security nightmare for any company. You cannot have both open source software and open internet, okay? Just look at the Polyfill.io malware scandal that just hit. Polyfill.io was in like a gazillion sites, including banking websites. It was taken over and malware was injected. And you can minimize the impact of those things by not allowing internet access by default. So when you deploy a Lambda, it's just blocked, right? And then, but the problem is that a lot of times you either need to open up private services in the cloud so you can access your service mesh, or you may need to access a public service. And it's a little bit easier with private endpoints, but in general, you still have to set up, like if you do need to access the internet, you're going to need an Elastic Network Interface in ENI. You're going to need a NAT gateway. And you're going to need private subnets. And this is a whole nother layer of complexity to ensure that when you deploy your Lambda, it's only allowed to access the resources it needs, right? And the fun part about, at least it used to be, I don't know if this is still the case, but like NAT gateways work off IP addresses, not DNS names. And so if you have services that have dynamic IPs, you need another fucking solution to manage that for you, And so it's like, I just want to write a one-line Hello World Lambda. And look at where we are already. And then the next part, the fun part, is you need a log system. Like CloudWatch, by default, will come with, like Lambda will come with a logging solution. And for one Lambda, that's probably okay. There's not much you have to do there other than enable the logging. But in most cases, like in a company where you're doing this for real, you would have a centralized logging solution. You'd implement an Elk stack, or you'd do Splunk or whatever. And that's another layer of complexity of how you actually propagate those logs into a centralized logging solution. That's required so you can troubleshoot anything that goes wrong in your application. You can see maybe stack traces and errors that aren't being handled. And that can alert you about issues that you need to resolve. And lastly, and again, this is a naive deployment. This isn't what I would even consider like full production grade. You need a telemetry system for measuring performance like AWS X-Ray. Right, so I need to know, how's my Lambda performing? Where are my bottlenecks? How can I are my users being, are they getting a bad user experience, etc. All of that crap to deploy a one-line application in the cloud and actually manage it, right? So how do we measure this complexity? And what is the cost of that complexity? And with each level of complexity, as it grows, let's just think of an exponential curve here, the likelihood of failure also increases exponentially. Right? So as you can see here, like if you're a company and you're basically saying, well, GCP does all that, I'll just deploy it on GCP. They've got services. Well, it's not that freaking simple, And what's great about Foundry is all of the things I just mentioned are managed for you, right? On your behalf. You don't have to write a single fucking line of that crap. You have to deal with any of it. I can deploy Hello World in about 30 seconds. So let's go just jump in and take a look at how we do Hello World in Foundry and how much easier this is to manage and how all this crap is managed on our behalf. All right, so we are going to blaze through this. First thing I'm going to do is just create a new code repository in Foundry. This comes with integrated GitOps and GitHub, meaning I can do CI/CD pipelines. I can do unit testing as part of that, and I can also set branch protections and deployment automatically. It's all integrated into code repositories. I can also integrate my own repos if I choose to. I'm going to choose TypeScript. This is the equivalent of the Lambda example we were kind of going through. You can also, in other stacks and newer stacks, you can choose Python as your runtime. I'm going to go ahead and just call this a test repo. We're going to go ahead and initialize the repository. And we're just going to wait for this thing to load. I'm going to come in here and we are going to blaze through this thing as fast as possible. I have an index file. The test directory works off Jest. So if you're familiar with Jest tests, you can go ahead and write your tests for your function there. The Jest config is here, although at this time you can't modify it. It's part of the build process, so you're going to get the settings that Palantir applies. So if you want to build tests, go for it. It's totally up to you. The way functions get deployed in Foundry, it's a little bit different than Lambda. It's not about writing CloudFormation. It's infrastructure from code, not infrastructure as code. So I'm going to go ahead and, in the example here, I'm just going to comment in the required API to write hello world. All functions must be declared as public instance methods of a class in Foundry. So, but I can show you how to apply functional programming to this in the future. That's how all of my stuff works. I use a lot of composition and function pipes in my code, but the entry points are exposed as class methods. So just a requirement, you have to do it. We're just going to write a simple hello world function. So I'm just going to get rid of the object set API, right? Our goal here is to showcase how we can do hello world. We're going to change this to a string, and we are going to go ahead and just return hello world. Let's say hello world. Foundry, let's just say Foundry is, what we want to spell, right? Foundry is awesome, right? That's what we want to say. We're going to go ahead and return that, and then what we're going to do is we're going to go ahead and just commit this as a change, right? And I'm just going to say hello world is my commit message. Again, this comes with an integrated GitOps environment, meaning the GitHub repo is managed by Palantir. All of the branch protections and running of unit tests and pipelines, it's already built for us. Our unit tests will automatically be run upon commit. What's going to happen here in a minute is you're going to see checks spin up in the background. And what checks is that's the CI/CD pipeline running. It's going to look for any of my tests that I have in the test directory. If I have any, it's going to go ahead and attempt to run those. As you can see, they're just stubs right now, so you can fill in whatever you want. And then if those tests pass, I can go ahead and issue a new release, right? And so we're going to go ahead and run that. Basically, we're just going to call this, there's semantic versioning in here. You can choose what you want to do. I'm just going to say that this is a major release. It's the first release of my repo. I'm going to tag and release. And then what I'm going to do is I'm going to go view the progress of this release process. And again, what's happening here is Foundry is running all of the checks in the background. It's making sure all the tests are passing. It's going to deploy it to production. And then it's going to be callable in my applications. Now, we just saw how much work it goes into this. And not only is there GitOps in here, all of the logging is handling on my behalf. Like all of the things that I was walking through before in the hyperscaler example, this is all integrated into Foundry. All right, function's published. It's ready to go. It ran, went through the GitOps process, published it. I can now use this function, and I can package it, which we didn't even get into, and I can package it, which we will get into in Foundry, as in a developer, using the developer console as a third-party application, meaning it adds like API gateways for me, which is a nightmare to do. It's not a nightmare, but it's actually pretty hard to do in AWS and other hyperscalers, where you need to put an API in front of your function, an API gateway, so you can call it from external APIs. I'll show you how to do that in Foundry, but this is it. I mean, literally like 30 seconds, I got a function up and running. It includes all of the things I was showing you before that are required, including the logging, including the CI/CD, all of that. It's all natively integrated. And if you want to work locally, you can. You can go ahead and click this work locally button. It'll allow you to copy the checkout URL. You can do a git clone, and you can work locally. There's even VS Code integration in here, so you can actually check this out in a web-based VS Code container and edit in there if you prefer that. So now that we have the function published, I do want to do a little bit more on the GitOps side. So I'm just going to build a basic test. We're going to go ahead and run that test directly in the IDE that's provided. And again, this is Foundry's IDE. You can work in VS Code, both web containers and also locally if you choose. You can see my test passed. You can also set breakpoints when you run tests, which is really useful. So like if I'm running a test and I want to see what the values that are being sent back from a function are, or otherwise debug my code, Foundry has a debugger that's integrated, and you can come in here and you can step through code and you can do all this great stuff, right? So like, look at all the things I'm not doing, right? There's a famous Ruby on Rails demo. Look at all the things I'm not doing. I'm not configuring GitHub workflows. I'm not having to set up CI/CD from scratch. I'm not having to figure out how I support web development with web containers and like other solutions from other companies. I'm not having to write, complicated publishing steps. I'm not having to figure out the release strategy and rollout and rollbacks. That's all integrated into Foundry, right? Look at all the things I'm not doing. And what that enables me to do is look at all the things I am doing, which is focus on business value delivery. And yes, Foundry is an opinionated ecosystem. It has opinions about how your CI/CD processes should work, your release strategies should work, how data integration works, which we haven't even got into in here. But those opinions, one, are largely correct, and two, are going to save you oodles and oodles of time and money to not have to implement in that hyperscaler layer. All right, cool. So now let's do a deeper dive on some of the GitOps integration and how this all works. We're going to go over to the repo settings, and in branches, you can enable branch protections. That's like the first thing most people are going to do. There's lots of settings here. I'm going to require at least one approver. Basically, going to say myself as the approver. This is kind of the equivalent of code owners. There's no support for paths. But it will require people, and then I'm also it will require certain people to approve pull requests, which gives you the equivalent effect in these repos. These aren't like super huge repos for the most part. Repo architecture is a whole nother subject in Foundry that should be part of your center of excellence team planning. If you don't know how to do that, reach out. It's something I do. But what I'm going to also enable here is allow users to approve pull requests they have created, because literally no one else to approve this thing but me. So I'm going to go ahead and initiate this, right? So I'm going to go ahead and save those settings. Now, with those settings enabled, if I go back to my main branch here, if I try to add another function, it's going to tell me I'm in a read-only branch. This is great. We want that behavior. We're going to go ahead and create a new branch, and I'm just going to do something like, I don't know, demo test, whatever. I'm going to create a new feature branch. Now what that's going to enable me to do is create my new feature and issue a pull request. So in this example, maybe I do something like, let's just refactor this to show a little bit of functional concepts. So let's just call this demos. And I don't have great names for things. So we're going to go ahead and just add an index file, index.ts, and then we're going to, I got to name it appropriately. Let's go ahead. I have two different size laptops, and the keys are laid out slightly different on both of them. So I get a lot of fudge factors in here. Let's go ahead and delete this file. Let's git key. Foundry adds those by default. It's so that empty directories don't get removed. I think or they're maintained. So you'll have to be deleting a lot of those. The next thing I'm going to do is just create a new file, and we're just going to call this hellos. .ts, and what we're going to do is just blow this away first of all, and we are just going to do an export. Let's call this hello sync, right? And we are going to say the return type is a string. And what's great, actually, the way we're going to do this, I don't need to actually declare my return type, and we are just going to return. You can use TypeScript to infer the return type. Foundry is really particular. Return types have to be explicitly defined in the main function that gets published, and they also use custom types. Maybe I'll show that in a second. But let's just say this is hello world sync, right? This is a synchronous version, and then we're going to do export function. Maybe we do hello world. Or we'll just call it hello async, right? And so we're going to go ahead and do that, and we're going to mark this as an async function. And we are gonna turn right away. This is bad practice. I just don't want to have to write set timeouts or return a promise. Well, you know what? Let's just do that. Why not? We can explicitly return a promise, right? Return new promise, and let's go ahead and type this thing out, and let's do accept, or what is it, resolve, reject. I haven't written promises manually in a while. So we're going to do a set timeout undefined yet. It is in the Foundry APIs. I'm not exactly sure why. TS ignore, and then we're going to define a function and a timeout. Let's just say 1,000 milliseconds. Hopefully I got this right. Again, haven't written set timeout in a long time. and we are going to resolve with hello world. And then, so we got 2 of these functions here. Now we're going to go ahead and just export them in our index file. Export star from dot slash. A lot of people use these are called barrel files in TypeScript that manage your exports. And so what it's doing, did I not define this right? Oh, hellos with a. This is a real common pattern in TypeScript. It's just so you can like have all your exports defined in a single place, and you don't have to like manually type every file. You can just type a directory name from where your imports come from. We're going to go ahead and come back to here, and we're going to go ahead and just import those. Let's go ahead and import, I think it's hello sync and hello. Hello. Why is it not picking up auto to Intel? I don't understand the Intel sense in. Let's go ahead and rename that too, by the way. I don't understand why Intel Sense doesn't always pick things up. Let's go ahead and call this one hello world async, and we are going to just return this guy, and then we are going to await this guy. Public, I believe you async these, and we're going to do a promise. I don't do a lot of class programming. Sorry, whoop. Okay, we're going to return await. I'm just going to go ahead and put it in a variable. Okay. Let's see, result equals await hello world async, and we're going to return this guy. All right, and then we're just going to move over to live test. Unknown is not assignable to type string. I don't know where this error is coming from. Index line 18. Which index file? Is there a line 18? Oh, it can't infer the type. That's interesting. Let's go ahead and just type it. Usually, I always thought the inferred types actually worked. Oh, I know. Oh yeah, it's because I'm manually resolving a promise here. Normally, it can infer the type from these async functions. I think in this case, because I'm returning a promise with call to resolve, it doesn't know how to infer the type because there's no return statement, which makes sense. Let's call hello world async and just run it and see like if I get anything back, if I broke things. Oh, works. And if I come over here and we run this, great, that's awesome. We're going to go ahead and update our tests. We want to do a test async, so we are going to do a test async, and we got to import, or we don't have to import, but we've got to call hello world async, and we need to do, let's just do a result. I like putting things in results for some reason. Const result equals await this, and we want to expect this to equal, what does it equal? This just says hello world. I kind of liked the old values better though. Let's change those around. Hello world Foundry is awesome. Hello world async, just so we know. Let's just put that in our test. And we're going to go ahead and run our tests again just to double check that things actually work the way we intend them to. Let's go ahead and test that. Let's see if we get any failures. Two passed. All right, we're looking good. Tests are running. We're going to go ahead. So what this is an example of is how to use like functional programming styles in this inside functions on objects in Foundry, or functions generally in Foundry, where they require a class declaration. I'm not a big fan of object-oriented programming in JavaScript or TypeScript. Prefer functional programming. It aligns more with React, which I do a lot of programming with, but also just my own sort of journey in JavaScript. Used to do a lot of prototypal inheritance stuff in JavaScript, and I learned a lot about the fact that there really aren't classes in JavaScript. It's a whole bunch of bullshit. The whole class layer is kind of a bunch of bullshit. I prefer functional pattern, and so when I have to work with these object-oriented interfaces, I prefer to just decompose them out into functions, and maybe I'll do some functional programming with composition. so that I can easily compose my apps from smaller atomic kind of functions. So if you want to do that, go for it. This is how you do it. This is very easy to do. We're going to go ahead and commit these changes. I'm just going to do more demo work because I don't want a descriptive commit message. Now we're going to go ahead and propose some changes, right? So once these are committed, now I can actually propose changes. And this PR is cool, right? Now, normally you would write a description of what's in your PR so other people can review it. We're going to go ahead and create this. And once the pull request is created, it's going to start running my checks, right? And it can show you here like, hey, CodeStrap's got to approve this thing. I'm going to go ahead and approve it. And then checks are going to run here in a little bit, which are going to run my tests. In the interim, I can come over here and I can see my changes, right? And again, look at all the things that I'm not doing. I'm not integrating GitHub Enterprise, right? And if you want this mirrored in your enterprise GitHub from here, you certainly can do it. Foundry supports external repos through mirroring so that your code can be co-located in the place of your choosing. But what's great is I'm not having to orchestrate any of this, right? I'm not having to go ahead and set up that GitHub job to run. I'm not having to set up GitHub Enterprise. I'm not having to do any of that. If I sit down day zero and just use Foundry's Git implementation, explain to me the problem. Other than code co-location, maybe you want that code living at some other place in your organization. But the idea that I would rather go implement GitHub Enterprise or GitLab or whatever, no, I wouldn't. I wouldn't rather do that unless there's a really good reason. Maybe I need a merge train from GitLab. That'd be about it, or some other more advanced features that might not be in here. For the most part, though, I think people got to wrap their brain around the concept of good enough software that meets the needs of the enterprise versus let me go build this thing for no reason whatsoever other than it's cool, which engineers love to do. Check out this interview with Sham recently. He touches on that as well. It's something I've seen throughout my whole career. It's why abstraction is so popular rather than just copying code. Everyone thinks the dry principle should be applied to everything. You wind up with code bases that are unmaintainable, get ripped out. Dan Abramoff gave a great talk on this. Engineers love to engineer, right? But at a certain point, you need as a business to understand the concept of good enough software. And the fact that if you have something like this, what are the benefits of your thing that's integrated with all these other things over just using this thing, which is super secure, meets all security requirements that I'm aware of, and integrates with my data, and enforces things like egress policies on these repos. You can't just call the internet from functions here. You have to attach an egress policy. We'll get into that in future demos. But there are so many advantages to just working here. And now you can see my PR is there. It's approved. It's ready. We're going to squash and merge it, which is a whole nother thing, by the way, that developers often don't do. They don't use the right merge strategy and get really crappy commit histories. So Foundry does a lot of things on your behalf to make all this stuff easy, right? Again, look at all the things I'm not doing. I'm not sitting there with these YAML files and GitHub jobs and testing those and seeing if things are breaking. This is all just managed on my behalf. And I can focus on the thing that the business actually cares about, which is the logic I'm writing here, right? The systems orchestrations and integrations and workflow automation. That's what the business cares about. Deliver the business value. They don't care about the freaking engineering, the undifferentiated heavy lifting, all of that. So this is going out. We're going to go ahead and, again, tag a new release. I'm going to call this a minor release. We didn't change any of the APIs. We just added new ones. And so I'm just going to call it a minor release. And that is going out the door. So one thing I didn't cover that was in the hyperscaler example is the need for private subnets and managing egress. And Foundry has that, again, natively done for you. You don't have to go through all the hassle of trying to manage DNS, etc., dealing with transit gateways and all that stuff. There's sources, and you can attach a source that's been defined here. You can see that I have a API source set up here, which is the Foundry API source. You can go ahead and attach these to your functions repository, and that will set up the appropriate egress for you to access those data connections, right? And in this case, if I can, let me just remove this because there is a problem with that policy. We'll go over to data connections and just jump over to that actual connection. Let's see where it's at here. I think there's no API name configured for it. I don't want to get into just setting these up right now. I don't know why the API name is not configured. Let's just go ahead and configure. That should have been configured by default. What this is doing is it's exposing a named like a DNS entry, right? And so this is like my Foundry stack URL. That's what it's exposing, along with the bearer token for the stack URL, and it's configured in their secrets manager. And what this is doing is opening up an egress policy to allow that function to communicate to this domain, right? And then I can send API requests. And that is the equivalent of having to do that in AWS, Lambda, or similar when you need private subnets. Again, is you have to attach an Elastic Network interface along with a NAT gateway, and you have to manage those using IP addresses. And again, if you need DNS support, and there's dynamic IP addresses involved, you got a whole nother layer, another ninth circle of hell you've got to figure out what you're going to implement. All this is just managed for me. I've got egress policy, I've got security. All of these are secure by default, by the way. And what's cool about that is within your organization is you can really strictly control the reasons why developers want an egress policy opened up. There's even this thing in Foundry called Foundry Checks, which helps with your SOC 2 compliance and other compliance policies, where it institutes an automated process when a developer or anyone else wants to apply a change in Foundry. They have to. You can set up a process for them to document why they need it, and it will automatically be recorded so that you can see like these requests to open up egress policies or other changes. Those going through Foundry checks before they even get approved. And then once approved, that egress policy can be created. So you get a lot of security by default. Plus you can deal with DNS and dynamic IPs, which is like a huge, huge time saver. On the subject of secrets management, this is one area where Foundry probably is a little deficient. Again, this is more like using secrets in things like GitHub or whatever. When you use a service like AWS Secrets Manager or some of these other officially provided secrets manager from hyperscalers, they use these things called, well, not all of them, I don't say all of them, but I know that some of them use hardware security modules, and HSMs are specially designed for storing secrets, and they will self-destruct upon like device tampering, and they meet all compliance, regulatory compliance for secrets storage. They literally have like these compliance officers that go around and will check boxes on whether or not this secrets management system complies with all the laws that are applicable for the industry they're in, etc. So secrets management is one area that Foundry doesn't fully fulfill if you are under strict regulatory guidelines, and so you would probably still want to implement a secrets management solution with a backing service that uses HSMs under the hood. This could be one area where Palantir could probably excel. I think there's a lot of areas where if they got into providing their own infrastructure layer, they could really advance, like way faster LLMs built with things like Grok or Etched AI chipsets or other types of things. Maybe one day Palantir will get into this, but regardless, if you need HSMs under the hood for secrets management, you're still going to need a solution for that. So it'll be like the one component out of the hyperscaler example that isn't natively supported in Foundry. All right, so there you have it, breaking down just how easy Foundry makes it to orchestrate hyperscalers and drive that complexity to zero. And I'm going to leave a link to this video by Chad as well. He does a great job of breaking down all of the complexity in modern data architectures and data processing. Now Foundry drives all that complexity to zero. I mean, you can see here all of the various components from the hyperscalers and other technology vendors that need to be stitched together to derive an ounce of business value, and Foundry gives that to you on day zero. I think it's a really deep subject. I'd like to do more videos on this topic, so I'm going to, along with some Medium articles. And I really think that this is our time. This is what Palantir is all about, which is like, let's all stop doing this undifferentiated heavy lifting of complex distributed system design on top of hyperscalers. Let's give you an operating system that manages that for you, and let's focus on winning, right? There's another great interview from Shyam Sankar today, the CTO at Palantir. I'm also going to leave a link to in the description that talks about this. And I think this is just as important as the migration from data centers to the cloud. We need cloud operating systems that really allow businesses to start extracting more value from their software systems. They cannot be spending oodles and oodles of time and money on platform engineering teams whose only job it is to orchestrate the hyperscalers. Right? So this new layer is also something that Databricks talks a lot about, and Oli Godsey over there, their CEO, has been a forerunner on this. So it's not just Palantir. I think this is going to be a trend in software. You have products like Vercel, for example. You have other products like the serverless framework that are attempting to manage this stuff. So like a lot of companies have come along recently and said to developers, hey, stop punching yourself in the face, and why don't we focus on actually delivering things that matter to your customers, and we'll take care of that undifferentiated heavy lifting in the architecture, design, orchestration, etc. So I do think this is a broader trend in the industry. I think Palantir is way ahead. I think Palantir is the only true cloud OS for enterprise software development. And so yeah, look forward to some more videos on the subject. Definitely watch this video from Chad, and have a great holiday weekend.